Okay, today I'm going to talk about the last norm function. We've had pnorm, we've had rnorm, dnorm gives the density, and now there's qnorm. These are the four R functions, and I'm going to talk about qnorm today. Well, I'm going to introduce it by way of an example. Let's have a look at this. There's my Gaussian. Let's just say I want to find a sort of reasonable upper limit to the Gaussian. I want to find how far you've got to go until only 5% of your distribution is greater than that value. So 5% is in here and 95% is in here. So I'm going to call it x, and x is a sort of reasonable upper limit. It's not an absolute upper limit because, as we know, the Gaussian distribution carries on forever. Why do I choose 5%? Well, because it's a sensible value and lots of people like it. I could have chosen 99% and 1%, but let's just stick with 95%. So let's just have a look at that. There it is. And I've got my 5% there. See how I'm not scared to write it out again and again and again, just to drill it into my head what's going on. 95% there. How far's that? Well, let's have a guess. Let's say x equals 2.1 standard deviations above the mean. Let's just have a look at that. Is that going to work for... This is a standard Gaussian, so the mean equals 0 and the standard deviation equals 1. And I'm going to guess it's 2.1 above the value. Well, let's see what the value is. And we know how to work out this area here. If that distance there is 2.1, we use pnorm of 2.1, and that gives me this area here because we covered that in the previous screencast. So let's find R and have a go. Here it is, and we guessed 2.1, didn't we? Was it 2.1? Yeah, 2.1, there it is. So let's try. Pnorm, open brackets, 2.1. That gives 98%, 98.2%. So that's too big, because we've only got what's left out of that. If I say 1 minus this, 1 minus that, that's only, oops, I'm having difficulty controlling this. It's only 1.7%. So we've gone too far. Let me draw that diagrammatically. It's a lot easier to draw it on this application than it is to draw R. What I've got here is something like this. That's 2.1, and this little area here was it 1.7%? Roughly it was, and that's going to be 98.3%. So we've gone too far. Specifically because this guy here is bigger than 95%. So 2.1 is too big. Let's try 1.3 instead. Let's try that. So if I go back to R, we can just try that. Pnorm 1.3, which is about here on this graph, I expect. 90%. You see, it's 0.90. So that means that we've got 90% on the left. I'll draw it. Do this. So we're going about that far there. There's 90% there, rough figures, and 10% there. And that's how far have we gone? We've gone 1.3. Well, I could zoom in on it. I could say, well, it's bigger than 1.3 and smaller than 2.1. Let's try 1.5. Let's try that. In fact, I'll do that. Bink. Here it is. Pnorm 1.5. 93%. So you see, it's 93% and 7%. So it's bigger than 1.5 because we're looking for the 95th percentile, I guess the proper word is. Remember that we're looking for this. We're looking for this x that's got this property here. There's x, and there's 95% to the left of it and 5% to the right of it. And we've guessed too small and we've guessed too big. So we know we've bracketed the answer. We know it's between, what was it, 1.3 and 2.1, but that's not very good. And of course I could play games like this all day. But the way to do it is to say qnorm 0.95. And this qnorm says what value of x has 95% of the probability to the left of it when you're considering a standard Gaussian. And it comes up to be 1.644, whatever it is. There it is. Well, let's just try that. Well, if that's the case, p norm of 1.644854 should be 95%. Aha! There it is. You see, 95. Oops. There it is. Oh, it's going to drive me nuts. There it is, 95%. So that's wonderful stuff. So this Q norm here, it enables you to go backwards. It's an inverse to P norm. Well, I guess we should really verify this. If I say table, oops, of R norm of 1,000,000, and I'm going to ask what proportion of them are greater than 1.644854. Where do I get the number from? I'm just copying. I'm just copying off here. That number here is just cut and pasted from there. Well, it's not cut and pasted because I typed it in. So what should we get? Well, it should be 5%. We should get 5% of that million. Let's have a look. There we go. So 5% of 1,000,000 is 50,000, right? And we get 50,000 and a tiny, tiny bit extra. And look, that should be 95 or 950,000, I guess. And look, it's 949,800 and something. So it's pretty close. I'll just do it again, just to emphasize that these are random numbers. And you see 49, so you see it's slightly above. You see it's slightly above 50,000 and slightly below here. So that's pretty good evidence. I want to encourage you to think like I do, and when you come up with a result, ask yourself, how can I verify this by numerical sampling? There's one more way which you can do it. If I ask P norm, Q norm 0.95, we should get back to 95%, because Q norm says what value of x has got 95% of the probability to the left of it. That value of x, P norm says what probability is to the left of it? Well, we know the answer. It's 95%. Brilliant. So that tells you that, well, it doesn't tell you anything to prove it, but it's just a nice little check. There's another little thing which you can do as well, which is to type Q norm 0.5. What value of x has half the probability to the left of it? And well, I'm going to draw it. Just a minute. If I draw my Gaussian distribution, there it is. If I say we've got 50% here, or half, I guess, and half there, well, we know that x equals 0. Of course we do. Of course we know that x equals 0 because the standard Gaussian is symmetrical about x equals 0. So let's just try that. Q norm of 0.5 should be 0. There you go. And it is 0 quite accurately because, well, it says it. It says it. What about 0.9? We did this one before, didn't we? 1.64 standard deviations. What about 99%? 2.32 standard deviations. See, it's a little bit bigger. There's just one more thing I'm going to do, and then I'm going to shut up. Let's just say that instead of finding a one-sided value, let's just say I want to cut off two values here at this distance here, and I don't know what that distance is there. I'm going to call it x, and that's going to be x as well. And I want 95% to be in here. That region there has got to be 95%. I'm trying to shade it in neatly, but not doing very well. There it is. So if that's 95%, what's left? Well, 5% is left. And that splits into 2.5% on this little region here. I should use a different colour. I'm going to use red. There he is. 2.5% there. And 2.5% here as well. So that's there. Go back to black. And that's 2.5% there as well. So let me just redraw that picture. Oh, it's not very neat, is it? Never mind, you get the idea. So that's going to be 2.5% there. And this one is 90, no, it's not 95, it's 97.5%. Why 97.5? Because we've got this 95 here, plus that little tiny bit there, that other 2.5. So to get this value of x here, we need x equals Q norm of 0.975, because that's 97.5%. So let me just do that. q norm of 0.975, and that's 1.959964. So you conventionally call that 1.96. You conventionally call that 0.96. There's another interesting thing here as well. If I go q norm 0.025, well, what we've got here is q norm of, oh, that's a better one, isn't it? That's 2.5% on there. So if we ask, that's 97.5% there. So that gives me, that distance there is q norm 0.975. If I ask what q norm of 0.025 is, well, that's the value for which only 2.5% of the probability, 2.5% is there, and 97.5% is there. So that's a mirror image of this picture here. So that means that x equals minus q norm of 0.975, because it's a mirror image of this picture here. Because we're going as far up from 0 in this picture as we are down, so it's a negative relationship. And I'll just verify that here. And what we're expecting is minus 1.959964. There we go, minus 1.959964. The reason I do that is just to check that our understanding is correct. And you'll see that as I'm talking about new concepts, I'll say, well, what we'd expect to see is that q norm of something is minus q norm of 1 minus that stuff. Oh, that's a bit difficult to say. I'll give you another example. Q norm of, let's say, 0.3 is that, minus 0.52 whatever. Q norm of 0.7 is going to be plus 0.5244. Okay, and I'm going to stop there. That's q norm.